So here's section 4.4, example 2. This is definitely worth looking at. So they say here's a definite integral involving an absolute value, and they just want to do the integral from 0 to 2 of the absolute value of 2x minus 1 dx. Now, the issue here is this absolute value is actually a piecewise defined function. And so, the absolute value of 2x minus 1 is equal to, well, it's 2x minus 1 as long as 2x minus 1 is greater than or equal to 0. But then it's the negative of that, which would be minus 2x plus 1, whenever 2x minus 1 is less than 0. And so we can look at these two pieces and see that 2x minus 1 equals 0. That happens when 2x equals 1 or x equals 1/2. And so we can solve those inequalities the same way. Never are we dividing by or multiplying by a negative number when we do that, and so they'll just work out that way. So what we have is that this piecewise defined function, this is equal to 2x minus 1 when x is greater than or equal to 1/2, and it is minus 2x plus 1 when x is less than 1/2. And so, since our definite integral here, the interval 0 to 2 contains that spot where the switches, actually we have two different integrals. And so we have to use this idea here, our theorem, our summation theorem that says this definite integral can be written as the integral from 0 to 1/2 of the absolute value of 2x minus 1 dx plus the integral from 1/2 to 2 of 2x minus 1 dx. So as they look here, it doesn't look like I've done anything other than make twice as much work for myself. But the key is this function evaluates differently, right? Depending on which one of these two intervals I'm in. And so the integral from 0 to 1/2, this function is actually minus 2x plus 1 dx. And then here, plus the integral from 1/2 to 2 of 2x minus 1 dx. So there we could drop the absolute values because nothing changes in their each respective interval. So we do this first one. We need the antiderivative. Well, the antiderivative of this is negative x squared plus x, and we're going to evaluate that from 0 to 1/2, and then plus here our antiderivative is x squared minus x, and we're going to evaluate that from 1/2 to 2. And so this is minus, and be careful about negative signs and so forth, so minus 1/2 squared plus 1/2 minus, well, not going to really do much with this, right? 0 squared minus 0 squared plus 0, so not much happening there. So that was our first part, and then plus we have 2 squared minus 2, and then minus, and I'm running out of room here, we put in the 1/2, so we have 1/2 squared minus 1/2. And so we evaluate that whole thing. I have minus 1/4 plus 1/2. And that's everything there. Plus, and I have 4 minus 2, which is 2. And then minus 1/4 minus 1/2. So this evaluates here to what, 1/4, and then plus, here we get minus 1/4, and then there's a minus, so this is 2 plus 1/4, and so this gives us 2.5 or 5/2. Alright, so 5/2, either one of those. And that is our antiderivative. If we look at the picture of this function, this function kind of comes down like this, goes like that. That's at 1, that's at 1/2. By the time we get to 2, again that was 2x minus 1, so that'd be a height of 3 here. And we could think of that definite integral as those areas. And so this area here, we have a triangle that's 1/2 by 1, so that area is 1/2. And then this triangle is an area that is 1/2 times 1.5, so 3/2 times 3, so I better write that one down. 1/2 times 3/2 times 3, and so that is 9/4. Oh yeah, see, I even messed this one up, right? 1/2 times 1, all times 1/2 is 1/4. And so we add those two together, we get our total area is 1/4 plus 9/4 or 10/4, which is 5/2. So looking at the geometry, we see that yes, we should have gotten 5/2. All right, so there's example 2.